Okay, welcome everyone to the 2020 Accelerated Artificial Intelligence for Big Data Experiments Conference. My name is Elio Huerta. I am the director of the Center for Artificial Intelligence Innovation. And I want to start this conference by saying a big thank you to the members of the Scientific Organizing Committee. If you have had the opportunity to browse the agenda, you will realize that there are four main themes for this conference. And the first one is astronomy. And I want to thank Andreas, Brad, Janice, and Sinan for their support and their suggestions to reach out to all of you to participate in this conference. In particular, Janice, she provided the idea of having a call for abstracts. And you responded very enthusiastically to this call. It is through these means that we were able to engage with scientists in Europe, across the US, and the response was really good. So if you're giving a talk as part of the astronomy theme, make sure to send all of them a thank you note. For multi-messenger astrophysics, I want to thank Eric, Margaret, Raf, and Jane for reviewing the abstracts, identifying the speakers, poster presenters. It was a very difficult task. I was in the meetings when they were selecting the speakers, and all the submissions were outstanding. So a big thank you to all of them for making the difficult decisions of identifying the presenters in this conference. In high energy physics, Javier and Philip, they did everything related to high energy physics, a lot of work, and it was only two of them. So make sure if you're a speaker as well to send them a big thank you note. Another theme in the conference is related to community building. And here we have different flavors. Brendan McGinty is the person that is our expert in connections with industry. He leads the industry program at NCSA. Daniel Katz, well, he's very important for this conference because he's the connector to many different communities, whether it is high-performance computing, scientific software, connections with the high-energy physics community, with multi-messenger astrophysics. He was the connector to many of these disparate communities. Vlad Kindratenko, he is very well known for developing and adopting innovative hardware for different applications, and more recently for artificial intelligence. And he's also a good connector to the companies developing this hardware. So his work finding the speakers and also providing expertise about how to engage with the developers of these technologies for AI has been very important. Elise Jennings, she is our connection with Europe, and we benefited greatly from her expertise understanding that part of the community. And Judith Hill, she is our connection to national labs here in the US. So to all of them, thank you. And if you prepared your presentations, if you prepared the videos, the slides, etc., all of those were handled by Pam and Melanie. It was a lot of work. So again, if you have the time, make sure to send them a thank you note. So what are we going to do in this conference? Well, it is a 3-day, or if you want, a 2.5-day conference. And what we're going to be doing the first day has to do with listening to the community. So we want to hear from you about how you are harnessing innovative computing, artificial intelligence, and maybe other methods to try to address computational grand challenges in different fields, in astronomy, in multi-messenger astrophysics, and high-energy physics. And we want to understand how these different areas, though they seem disparate, they have different threads or commonalities. They have a lot of commonalities. So we want to understand this because at the end of the day, we want to find solutions that work very well for all these different fields. On day 2, we are going to hear from experts that are outside of physics and astronomy and who are interested in leveraging the tools that we're developing for these different areas. And so this is a very deliberate effort to create a Harnessing the Data Revolution Institute. We want to house in a single place expertise from physicists, from astronomers, but also from computer scientists and those that are developing the next generation of innovative hardware for artificial intelligence. And we want to understand how all of them can benefit by having a cross-pollination of experiences and expertise. And so we are going to hear from people from geoscience, from industry. So if you're a student or a postdoc and you want to understand what is it that companies want to see in an applicant, we will have the director of data science from Phillips 66 talking about this. So this is the goal. First, we understand about what is happening in the community, and then we want to see how we can reach out to a larger community. And this will be important as well to figure out how we can better engage with industry. Because I'm sure you have realized, even if we stopped doing AI today, in industry this will continue, because it is industry, the field that started the application of AI at a scale for big challenges. So we need to understand also how to benefit from developments in industry. And finally, in day 3, all those that are excited about working with us towards the creation of these institutes, we're going to get together for half a day, and then we're going to draft a plan so that we create a team, a solid team, that will go and compete for one of these institutes in the spring of 2021. So I hope that you join us on Wednesday, and you hear from us about our plans that we have for several town halls leading to the spring of 2021. And you participate actively in these activities. If you want to collaborate with us on the projects that we have, you're most welcome to reach out and understand how we can accomplish that. And finally, I just want to thank our sponsors, the National Science Foundation and NVIDIA. And having said this, I'm just going to hand this over to the first chair of the following session, who's going to be Janice. So please, Janice, take it away.
Thank you, Elio. Can you hear me? Great. Welcome, everybody, to the first session. And thank you, Elio, for all of your leadership in organizing this conference. Our first session today is entitled Big Data and Computational Grand Challenges in Astronomy, Multi-Messenger Astrophysics and High-Energy Physics. And the way the session will be structured is that it is divided into 3 sections: astronomy, multi-messenger astrophysics, and high-energy physics. And what we'll do is have all the speakers give their 5-minute presentations, their summaries, and then have a 15-minute Q&A all together for all of the speakers after the group is done. Each section has 6 speakers, and a longer version of their talk is posted on the webpage. And so if you want more details, please go and review their more detailed talks. Okay, then. Our first speaker of the morning is Ryan Hausen. And Ryan is a graduate student at the University of California, Santa Cruz. And he'll be telling us about Morpheus, a deep learning framework for pixel-level analysis of astronomical image data.
Good morning. Can you hear me okay?
Yep.
First, I'd like to thank the organizing committees and the sponsors. I really appreciate you taking the time to listen to this talk. Again, I'm Ryan Hausen, and I'm going to talk about some work that I did with Brant Robertson at the University of California, Santa Cruz. Specifically, Morpheus, a deep learning framework for the pixel-level analysis of astronomical image data. I want to motivate the talk by showing this beautiful image from Hubble to show that astronomical data are richly complex. Stars and galaxies can be bright, they can be dim, they can be very, very big, they can also be small, and they can be overlapping one another with varying levels of opacity. Additionally, the native image format for astronomical image data isn't PNGs or JPEGs, so you have to work with the data the way that it comes. Compounding this complexity, we have upcoming telescopes that are going to deliver more data than we can handle using human means alone. Given the James Webb Space Telescope, Vera Rubin Observatory, and Roman Space Telescopes are going to produce very wide and very deep images, and Vera Rubin specifically is going to produce terabytes of imaging data every night. And so we need to find automated machine learning methods, or machine learning or not, but automated methods to address these issues. There are two tasks that I want to talk about specifically in astronomical imaging. The first is detection. And so, for example, in the image on the right, detection would be, where are the objects or sources in this image? And for example, that might look like this. And the other task I want to talk about is morphological classification. And that tells us, given a specific object or source, what is its morphology or shape? And that might look something like this, with different classes describing different kinds of shapes that we see for sources or objects. It's important to note that these two steps are done separately. Traditionally, we find the sources, we do some intermediate processing, for example, converting to JPEG or PNG, depending on the method we use for morphological classification, and then we do morphological classification. With Morpheus, we do detection and classification simultaneously and at the pixel level. So what that looks like for this image you see here again is this. So every pixel in this image has been classified with a particular morphological classification. And the black pixels you can see define background pixels. You can see that the pixel level morphology gives us a rich visual composition of what morphology is like, and leans into the fact that we see morphology in the galaxies that we look at. Also, we work in the native image format for astronomical image data fits, so we skip the intermediate processing step. We do this with a UNet, which I'll go over quickly, just provides, given an input image, provides a classification for every single pixel in the output image, and is a type of convolutional neural network. We do segmentation and deblending using the background classifications from the model, and segmentation and deblending are also done using the watershed technique, the original flux in the image, and a Sobel filter. We do cataloging, taking pixel level classifications and bringing them up to a source level by combining those classifications within a source using a flux weighted average, which we found to work intuitively well for combining pixel level and bringing it up to source level. And it works well at scale. So we did the whole candles field with the Morpheus framework package, and that's over 2.4 billion pixels. Each of these was classified using the Python package we released and is done using one single call. And Morpheus handles the parallelization, splitting things over NVIDIA GPUs or over CPUs for you. It's a very much point and click as close as you can get to that with programming. So in summary, Morpheus detects and classifies simultaneously and does so at the pixel level. It scales to terabyte-sized image data, and we think that this technique could be used for other methods like photometric redshift. The code is open source, it's pip installable, has a Docker image available if you use Docker. We have a website, an interactive map, morpheusproject.github.io/Morpheus. The paper is on the archive, and we were recently featured in Nature Astronomy as a research highlight. And with that, I would like to conclude my summary.
Thank you, Ryan. Very, very interesting. I'm sure people have a lot of questions. I have a lot of questions. The next speaker is Dimitrios Tanoglidis.
Hello, thanks for the invitation. I would like to present a deep learning method to separate low surface brightness galaxies from artifacts using deep learning. Thank you very much for the invitation. So let me start by briefly explaining what are the low surface brightness galaxies and why they're important. So by definition, these are diffuse galaxies with a surface brightness that is at least 1 magnitude fainter than the ambient sky. So by their very definition, they are very, very difficult to detect. And especially they're difficult to detect over a wide area of the sky and in different environments. And for that reason, it would be good to have a survey of them, and in order to be able to test models of galaxy formation and the galaxy halo connection in that regime. So I will present my work is related from data from the dark energy survey, which is a 6 years optical survey that just finished taking observations last year. And so we first created a catalog of low surface brightness galaxies from the first 3 years of DES. And we had 3 main steps. And by showing you these 3 main steps, I will show you, first of all, why detecting low surface brightness galaxies is challenging, and why we have to use at some point deep learning in the future when we go to even larger surveys, but also present you how we created a large training set that we were able to use for deep learning. So we started by applying some criteria in sizes and surface brightness, like source extractor criteria. But from all the candidates we had, more than something like 90% were artifacts, as those you can see here, some blended, like some diffuse light blended with smaller objects. So this was a very large fraction of artifacts. To reduce the size, we applied a machine learning classifier for vector machines on a visually annotated training set, again using features from source extractor. And we managed to reduce the number of candidates, but still those that were classified, from those that were classified as positives, almost half of them were still artifacts. So we had to visually inspect all of them to get rid of remaining artifacts, remaining false positives. And we ended up having a little bit more than 21,000 galaxies, low surface brightness galaxies, and an almost equal amount of artifacts. So in the process of doing that, of course, we had our catalog to do astronomy and explore, but also we had a large training tables. In the future, we will not be to things that we will not be able to visually inspect objects as we did now, because we are getting into the really big data era when, like, for example, the legacy surveys for space and time, where Rubin Observatory will inspect more than 20 billion galaxies over the 10 years of observations. So we used a convolutional neural network, a simple architecture, as I show here, of 3 convolutions followed by 3 dense layers to separate galaxies and artifacts. We tested more complicated architectures, but this simple one was working very well. So here are some examples of low surface brightness galaxies and artifacts that we used in our briefly show the results. So here you can see, first of all, that the convolutional neural network significantly overperforms other methods like random forest and subspectrum machines trained on features. So these are related, like these are performance of these classifiers on features, and these are directly on images. More results. So we reached an accuracy of 92%, and recall, or what I would like to call is like purity of 92%. So less than 10%, less than 9%, actually 8% are remaining artifacts in our sample. We tested the if we change the way we split our training, validation, and test sets. And that was the part that was very, very interesting, is that we used this, we used our classifier trained on DES data to classify data from the hypersupreme camera, that we had some low surface brightness galaxies that were published like 2 years ago, the results. So we trained on DES data and applied directly to hyper supreme camera, and we had a good classification accuracy. We'll show you later. But also we retrained on a smaller sample from that survey. So this is called transfer learning with domain adaptation, and we improved the results even more. You can see here like the two cases. Also here the two confusion matrices. So we have an accuracy of something like close to 80% when we directly apply the classifier trained on the DS data on hyper supreme camera data, but with the further training, we go up to 87%. So at that moment, I would like to thank again the organizers of this conference, but also I would like to thank my collaborators that made this possible in both steps on finding the galaxies and on the deep learning side.
Great. Thank you, Dimitrios. Okay, our next speaker is Christine Yee from the University of Washington, Bothell, and she will be telling us about searching for pulsars with AI.
So, hi, my name is Christine, and today I'll be telling you about improving radio pulsar searches with artificial intelligence. So just as a recap, in 1967, Burnell and Hewish found the first pulsar, and today the ATNF pulsar catalog shows 2,811 pulsars with nearly exponential progress in finding them. Goals of current pulsar searches are to find millisecond pulsars and relativistic binaries, which are really useful for testing fundamental physics, and also the other 99% of the galactic neutron star population that we still haven't seen. So even today's wide area surveys generate petabyte data and millions of candidates, which a lot of them have to be inspected by humans after very slow pre-processing. And next generation surveys and instruments in the 2020s and 2030s are really big data explosions because of the sensitivity requirements to find pulsars. So there will be thousands of potentially visible pulsars, and it'll process data above the writing limit, up to 1 terabyte per second with SKA, which means we need fully real-time processing. So the data volumes of both current and future surveys need AI and big data solutions. Some characteristics of pulsars that are important here are the period derivative, which is a measure of how fast it slows down, and the dispersion measure, which is a measure of the integrated electron density along the line of sight. So we see it as this frequency-dependent delay where these lower frequencies arrive later. So one approach to finding pulsars involves single pulse searches, where you search for individual bright events from certain pulsars called rotating radio transients. These are ones that are better detected in these singular events than with a pure periodicity search, possibly because not every rotation has a bright enough pulse. So here you can see two pulsars that are detectable with these single pulses, a lot of bright events from both pulsars. And then here you can see the location, known location of a known pulsar with no pulses detected. So when we look with single pulses, we start with a radio time series and then create catalogs of the single events. Then each radio beam can be searched for pulsars. So there are three main ways we would identify them. One is by looking at dispersion measure versus time, where we have these dense clusters of events at a certain time and dispersion measure. One would be looking at dispersion measure versus signal to noise, where we have these characteristic triangular peaks peaking at the source dispersion measure. And one would be the time versus signal to noise, where these line-ish structures just indicate we have a lot of events at once. So current methods basically involve scoring of different features like the peaks and clusters, and then inputting that into some sort of binary classifier. They generally perform well, but it does require manual selection of one set of hyperparameters and features for every single candidate, like to use the same ones on every candidate, which is not really well suited to a diverse population, especially one that varies a lot in brightness. And humans still inspect a large number of these candidates, which slows down the process. So I'll talk about two new approaches I've been working on. So astrophysical pulses tend to cluster in dispersion measure and time space, like I mentioned. And density-based clustering is optimal because it can identify noise points and also pull out the densest groups. But finding the optimal hyperparameters to automatically pull them out is hard. So if you look on the left, all of these are pulsars, but these ones have clustering that matches the actual pulses, and these ones clearly do not. So what I did was I incorporated Bayesian hyperparameter optimization, which uses Bayesian methods and sampling in order to optimize hyperparameters faster, into a pipeline running clustering on these plots. And I found that it was the fastest way to iteratively find the best hyperparameters. So challenges I'm still working on are figuring out which objective function to minimize to actually get clusters that match the astrophysical ones, and also emulating the actual full optimization process to speed it up more. I also worked on looking for these characteristic triangular peaks in the dispersion measure signal to noise space. So humans can pick these out really well, and object detections, which are aimed at finding objects and images, can very closely mimic human vision sometimes. So I use YOLO, You Only Look Once, which is an algorithm based on a convolutional neural network that is able to achieve real-time object detection and state-of-the-art performance. So I found it was really great at pulling out rotating radio transient, these peaks, when sorted into two classes, the ones with empty space in the middle that are boxed in pink, and that's usually just one or two big events. And these are more filled in green, that usually have many very faint single pulses kind of building up that triangle. So between the clustering and the peak detection, so these features aren't visible in every single rotating radio transient, but one of these methods is effective for almost every single one. So from this work, I do have a couple of rotating radio transients from just a couple days of Green Bank survey data, which is exciting. Just wanted to share that. And in summary, deep learning and AI are the future of pulsar searches. We really want to take human inspection out of most of the picture, and computer vision methods do seem to perform the best and are worth exploring more, both for periodicity searches and single pulse searches. We need to build up big, effective big data methods now where we can still afford to process with more latency, and then prepare to scale it up to work in real time so that we could find thousands of interesting and scientifically useful pulsars. Thank you.
So our next speaker is John Wu. And John is from the Space Telescope Science Institute. He's a postdoc there, and he'll be telling us about deep learning insights on the morphologies and evolution of galaxies.
All right, thank you very much. Big thank you to the conference organizers for putting together this wonderful program. It's great to hear talks from multiple scientific disciplines and combine that with AI. So I'm excited to discuss deep learning applications in astrophysics, and that's in order to understand how galaxies grow and evolve. So here is just a sequence of galaxies from the Sloan Digital Sky Survey, and they're actually arranged from the lowest metallicity, that is, they have the lowest amount of chemical enrichment to the highest. And you can obviously see that morphology, how their appearances have something to do with that. So, you know, we know, and we've known for a long time, that galaxies have very diverse appearances, from spiral galaxies with disks or bars to these yellow-red elliptical galaxies. And astronomical imaging surveys have transformed our view of the universe, which gives us a sense of galaxy star formation rates and masses just directly from imaging. Now, the image domain is very valuable for inferring some galaxy properties, but not all. And oftentimes we need to spend a lot more telescope time to take spectroscopic observations, which lets us see exactly how much light is emitted at specific wavelengths. And that tells us information about the different elements or ions in interstellar gas, from which we can infer things like the metallicity, the gas composition, or how much cold gas there is, or its ionization state, and so on. Unfortunately, as I said, spectroscopy is pretty expensive, so it takes way longer than getting an image. And fortunately, machine learning gives us an intuitive way to bridge that gap. We can connect the imaging to its spectroscopic view of a galaxy. So from an image like this one, we can determine not only the gas content, that is how much cold gas there is, but also the gas composition, so the metallicity, like I said before. And we can do that simply by training on those quantities which are derived from spectroscopy, for which we feed in these images into, convolutional neural networks, as previous speakers have mentioned. And this is really powerful, and it goes well beyond using galaxy morphology simply as a classification tool. And even more importantly, we're about to enter the golden age of wide field imaging surveys, which will detect billions of new galaxies. As was said before, the Rubin Observatory is starting soon, and later on, we're going to have beautiful new space-based imaging similar to the Hubble Space Telescope with the Roman Space Telescope, and it's going to have a greatly expanded field of view. So these great survey telescopes are going to detect billions of new galaxies, but there is no way we're going to get spectroscopy for all of these newly detected systems. And so AI is going to need to bridge that gap. And so in my talk, I'm going to emphasize 3 novel ways that we can use AI as a tool for discovery. I'm not going to talk about them now, but just mention this quick example where we show that we can feed in an image and not only classify a galaxy as gas-rich or gas-poor, but we can also highlight the specific morphological features that this algorithm is relying on in order to make such a distinction. And surprisingly, this works for not only color, but also monochromatic images. So you can really get a sense of the flexible image features that the convolutional neural network has learned. And as a bonus, this is not in my talk, but I want to say that novel developments in AI, such as neural network architectures, optimization, modern optimizers, and data augmentation, even transfer learning, as was mentioned, these allow us to make groundbreaking new connections between galaxy observables. And we present something recently in this submission to a NeurIPS workshop, Machine Learning and the Physical Sciences. And you can check that out in the archive link down there. But basically, we can directly predict galaxies' entire spectra from optical imaging. So in summary, please check out the full talk. It's on YouTube. It's linked in the agenda. And I just want to say, we're ready to make some huge discoveries in the field of galaxy formation and evolution, thanks to accessible and interpretable AI. Thank you.
Thank you, John. Okay, so our next talk is from Catarina Alves. Catarina, are you there?
Hi, yes.
Hi. So Catarina is a graduate student at the University College London, and she'll be telling us about classifying supernovae in plastic data with SN machine.
Hi. I would like to start by thanking the organizers for this conference. So the work I'm doing classifying supernova is in preparation for the Rubin Observatory Legacy Survey of Space and Time, or for short LSST. This survey will last for 10 years, and every night it will get roughly 10 million alerts. But we do not have the capability to follow up all of them. So we need to choose which events to follow up. And we need to do it in an automated way. In order to prepare for this challenge, the Photometric LSST Astronomical Time Series Classification Challenge, or for short PLASTIC, was launched. It contained a large dataset of simulated LSST observations for different types of transients and variable stars. And in this work, we focused on the supernova subset. The training data of this subset is unrepresentative of the test set, because typically photometric classifiers are trained on spectroscopically confirmed training data. Spectroscopy is more accurate, but we don't have the resources to obtain it for all the events. Additionally, it's easier to get spectroscopically observations of events that are closer by and brighter. So we see this disparity, this lack of representativeness between the training events and the testing events. But a classifier does not perform well when the training set is not representative. So in our SN machine pipeline, we start by generating a new augmented dataset. We fit Gaussian processes to our training set events. And then we withdraw new observations from the Gaussian processes to generate new synthetic events. Using some domain knowledge, we are able to generate the synthetic events at higher redshifts and then making the augmented training set more representative of the test set. The test set observations are also more uncertain, so we also degrade our observations in the generated data. And this approach was based on Boone 2019. But for our classifier, we use wavelet features. These are model-independent features that are localized both in time and frequency. And we chose an approach that's approximately invariant under translation and stretch. The advantage of wavelet features is that they are general. They are not model-dependent, and they work for various types of transients and time series events in general. For the classification, we use a gradient boosting decision tree classifier. But we need to take into account that when augmenting, our training set, besides being unrepresentative, is also in balance. So to improve the performance, we ensure that on the augmented data set, every supernova class has the same number of events. In the diagonal of the confusion matrix, you can see that most of the events are accurately classified. And we can look at the off-diagonals to see which events are being misclassified as what. In summary, the wavelet features are model-independent features that work well for many types of time series events. And to have a good classification, we need our training set to be representative and balanced. To have it representative, we explore the differences between the training and test set and come up with mappings that allow us to generate a new augmented data set that resembles more the test set that we want to predict. To solve the imbalance issue, we can simply generate more synthetic events for our less common classes. Thank you, and I would also like to thank my collaborators.
Okay, thank you, Katrina. Okay, so we have one more speaker in the astronomy session. Okay, it seems that the speaker is not with us at the moment. So what we'll do is, I see there are a couple questions in the chat. We'll be taking questions for all of the speakers now. So our first question comes from Ashley Villar, and this is a question for Christine. Ashley, do you want to unmute and ask your question?
Yeah, I'm happy to do that. Hi, Christine. I think that was your name. You had a great talk on pulsars. Yeah, you said that your current work was looking specifically for a nice loss function to check similarity, like between expectations of the pulsar clusters and what you're getting. I think that was the general question. So I'm wondering if something like KL divergence would be a good solution.
Yeah, I think that would definitely work to, I guess, check that my actual end hyperparameters are working well. But the thing is, I'd also need to make it work for data that we don't actually have a pulsar solution for. So for that, I'd want to measure that when you minimize it, it can just go to the what I consider ideal for a pulsar, which kind of changes from observation to observation.
Okay. Ashley, did you have a follow-up on that?
No, I was going to type something in chat. That answered my question.
Okay, great. Okay, let's go to John. Thank you, Ashley, for posting the link to John's paper in the chat. And John has a question for Ryan.
Yeah, thank you, Ryan. That was a really excellent talk as well. I was curious about how Morpheus could account for a smoothly, varying background. Is there any sort of pre-processing done for sky subtraction, or how's that parallelized?
So the images are science-ready images, which I believe did have the background subtracted. There are some, because of the size of the classifying window, if you get very large spheroids that get smooth, there is an interesting effect that I've seen, and I'd be glad to show some examples that you can see in the interactive map that I released with Morpheus. So I think that, yeah, it does generally well with background and low surface brightness, or lower than the training set, but especially smooth things can, if they're large enough, introduce interesting artifacts in the classification.
I have a follow-up question on that. So over the fields of view that you're considering, and we're really detecting small objects like galaxies, small objects that have small angular sizes. Why would the background matter since it is low and very slowly varying?
So I don't know how much it matters per se, because we also standardize the images before they're classified as we move through a window. But the images we used had the background subtracted, and I haven't run it on a non-background subtracted image. We used the HLF survey release, which was science ready for the catalog. So I'm not sure how much, but I don't want to say that it doesn't without having tested it.
Sure, right. Okay. Next, we have a question from Adriano. Adriano, do you want to unmute and ask your question for Catarina?
Sure. I would like to know, how do you compare to other papers where, because plastic, is something pretty common. So I read quite a few papers. So I would like to know, how do you do compared to other papers? Like, for example, your confusion matrix with respect to the confusion matrix of others.
Well, for some of them, they are similar. But for the papers that classify more classes, it's hard to directly compare, because when they have more classes to distinguish, is obviously a different problem.
Yeah, sure. Thank you.
Okay. And then we have Gautam. Is that how you pronounce your name?
It is.
Okay.
Hey, Janice. Ryan, lovely talk on Morpheus. I am particularly curious about how it does as the data degrades in resolution. So HST in particular has wonderful, 0.04 arc-second resolution. Something like Pan-STARRS from the ground is 0.25 arc-seconds, and of course has much more artifacts because it doesn't have the lovely drizzle data that you get from Hubble. How well does this work for ground-based surveys? Because I'm thinking ahead to LSST in particular.
So we haven't applied Morpheus to ground-based data in particular. I imagine it's not an unreasonable opportunity for fine-tuning or transfer learning. But having not run it, I can't be too sure. If the image is degraded, then you would expect on some level some degraded performance. But for what you have, I think transfer learning, which another talk showed has some success, could be an opportunity for that.
Okay, thank you.
Okay. Just a reminder, if you want to ask a question, please indicate that you have a question and for who in the chat. And you can unmute and ask the question or place the question there. Okay, our next question comes from Brad Whitmore, and this is a question for John. Brad, do you want to unmute and ask your question?
Yeah, it's actually just about the same question that just got asked, but yeah. I'm wondering, what kind of accuracies are you getting, and how dependent is it on either the distance or the size of the object? And thinking of an entire HST image of one galaxy, and how does that work? And then a very distant, Z of 2 galaxy that's just barely resolved. So can you say a little bit about distance and what kind of accuracies you're achieving?
Sure. Yeah, so for all the work that I've published so far is with ground-based telescopes, and so mostly from the Sloan sample, so that only goes out to redshift 0.3. I would say, though, that, even with the redshift evolution, there you have to account for things like size, evolution, and K corrections, which a neural network is able to implicitly learn. We have noticed that. In terms of accuracy, there are different tasks at hand. For classification, we can get something like 99%, whatever, if we have two well-defined classes like gas-rich and gas-poor, and you can see that in the paper. But I actually often work with regression tasks, and so one example of how well a CNN can do is that we're able to reconstruct the mass metallicity relation to within the intrinsic scatter that we knew of before, which is to say that we can reconstruct that scaling relation with no additional scatter based on regression results with the CNN from images.
Thank you.
That's pretty amazing. So presumably you have all of the metallicities that have been derived from the spectra, and those are linked to the spectra and then linked to the images that the CNN
Yeah, it's kind of perplexing. Yeah. We think that it's accounting for some scatter that we previously would have expected. Well, some from star formation rate, which we know can explain the scatter sort of along the fundamental metallicity relation direction, and then some which we think is morphological in nature. So it's not truly intrinsic scatter, but rather can be marginalized when you reconstruct a scaling relation.
And when you say you reproduce the scatter, I guess it's comparable to the scatter found in the
Christie Tremonti et al.
Right, the Tremonti paper. And the mass range presumably is that this is valid for is the same mass range?
Yeah, it's in the same mass range, although of course the scatter actually varies, as a function of mass, just due to the number of training examples. It actually, it reduces the scatter intrinsic to the empirical relation for the most well-represented samples. So again, perplexing, but we think that there's morphology can help explain some of that.
Has that been written up anywhere in paper?
Yeah, so I wrote a paper with Stephen Boda in 2019.
Okay.
In NRS.
Okay. Thank you.
Thank you.
And Eric has a question for Ryan.
Yeah, can you hear me okay? Can you hear me okay?
Yes, please go ahead.
So let's see. My understanding is that you have taken the approach of doing both detection and morphological classification in one step. I was wondering if you have, let's say, quantified whether that approach, namely doing all it in one pass, if you've quantified how better it is with respect to doing detection first, maybe with your similar methodology, followed by the morphological classification, and whether you have some sort of how much improvement you're gaining out of that. And maybe another quick question, I guess at the end of the day, it may be a question for all of us as we discuss about new packages and methods made available for the broader community. If I understand that if you're keeping track, let's say, of your user bases, namely other communities, or not even within your community, how your package is used, if you have feedback and related aspects of making available something that it is for the broader use. Thank you.
So can you hear me okay?
Yep.
Okay. With respect to the detection, we did compare the results using the Morpheus classifications and the deblending and segmentation algorithms within Morpheus to the 3D HST survey on the Good South image in our paper. I don't know the numbers off the top of my head with respect to accuracy, but there were some 3D HST has a better catches more faint sources than we do as things get really faint because the training set was on brighter sources. But interestingly, we were able to pick out some false negatives that the 3D HST survey did not pick up, especially with sources that are visually distinct but are close to bright sources that 3D HST maybe didn't pick up when they used the traditional method. So it's a really, really faint things that we didn't train on, we miss. but there are some interesting cases where we do well. And then with creating software, I think obviously, I mean, I'm an advocate. The code is available in Python. The code is open source, and the data is also freely available in open source. And in fact, the classification results, you could make your own classifier using our outputs. So I'm all for it.
Okay. Does anybody else have any questions? This is the last one that's posted in the chat, but we have a couple more minutes.
May I ask a question for Christine? Sorry.
Of course.
With the object detection part of your presentation and where you used YOLO, the peaks seemed pretty big. And do you know how that compares to other methods that perhaps don't use a CNN?
Sorry, could you clarify what you mean by like pretty big?
Oh, sorry. Just visually looking at the pictures where you have the bounding boxes given by YOLO, there seem to be two classes, but the peaks that YOLO predicts on and gives bounding boxes for, they seem like taller than the surrounding part of the image, if it's an image. And so I was wondering how your YOLO method, actually simply, how does the YOLO method compare to non-CNN methods?
Yeah, so the popular non-CNN methods are to fit some kind of like, some kind of just form to it that kind of matches the shape of the peak. But the advantage of YOLO, I think, is that like it can basically pull it out from like an infinitely dense plot, whereas those fitting actual functions to the peak would scale really terribly for high sensitivity searches where you're going to get a lot of events.
I see. Thank you very much.
Okay, last call for questions before we move on to multi-messenger astrophysics. And as a reminder for everybody joining us, posted on the agenda are links to the 15-minute talks that the speakers have prepared and we've posted. And these are just 5-minute summaries of those talks. And let's thank the speakers in the astronomy section of this first morning session again. They were all fantastic talks covering a very wide range of applications of AI in astronomy. Thank you.